fight the forces of nature. So basically, we're going to dive into how these airplanes work and how we'll see the rest of it. So these are the contents of the present of today's lecture. We'll have an introduction first about regarding the topic, and afterwards we'll see how this aircraft in the first place flies and how it remains stable, and we'll see what are the control surfaces that, in fact, control this aircraft and its motions. Then we'll go into the detail of these control surfaces, and then we will look into something called the microburst, which is the fighting about the nature part. It comes into this umbrella of microburst. So we'll see what this microburst is and what it does to these aircrafts, and what researchers and scientists have been doing to cater the effects of this microburst on these aircrafts. And we'll see how the technology is increasing safety day by day, and then we'll conclude the presentation. Uh, okay, so why airplanes stay stable in a constantly changing sky? So we do understand that uh, we encounter different types of weathers, and we do have very cold and harsh conditions while the airplane is flying from different parts of the earth. So, well, irrespective of the environmental factors, our our airplanes, well, they do very good, and they sustain a constant stable flight. So we'll see how that happens and what is the physics behind it, and how these airplanes fly in the first place. Okay, so then we will be looking today at engineering versus nature. So we'll look at one of the attacks of nature that we may encounter during a flight, and we'll see how our engineering work well, enables us to cater that attack. So we'll see who wins and how. So from basic flight to survival in extreme weather. So if we talk about how airplane works in the first place, so it is based on this Bernoulli's principle. Okay, so the way it works is this, that if we have an object flying through the air, and uh, if if it is flying to through the air, so it is going to disturb that air in such a manner that if there is some air at the top side of the wing that is passing by at high speed in comparison to the bottom side of the wing, then we are going to create a pressure difference, and that pressure difference will generate an upward lift force. So at the bottom of the wing, we have high pressure, slow air with high pressure, and at the top, we have fast air with low pressure. So from high pressure to low pressure, a natural push is encountered by this airfoil wing. So this lifts this point in space, and since this is attached to this airplane body, so the whole body lifts up. So it depends how much air difference is between these two coils, and we can lift huge amounts of payload using these airplanes. Well, they, they can go up to thousands of kgs as well. So airplanes are pushed, pulled, and shaken by the weather. Okay, so they by air, wind, and weather. So stability comes from smart design plus powerful control system. So the design is regarding the physical structure of body, and we'll see what are the major parts of this design process. And then ultimately, we'll see that pilot sometimes is not enough to control the aeroplane. So we do have to introduce some kind of advanced control algorithms to cater the errors that may be created by the pilot. Okay, so pilot continuously adjusts the flight to stay ahead of disturbances, but sometimes just pilot is not enough. So we have to rely on the machines, because and the decisions that these machines are going to make are far, far more intelligent than what a human being can perceive in real time and decide on what to do next. Okay, so moving on. So, if we see the different types of forces that acts on an aeroplane. So we have an upward force called the lift. We have a downward force called the weight. So weight is basically the weight of the aeroplane. And since the gravity is acting on this plane and it is flying in the air, so gravity is pushing it downwards. So we have a downward force that is because of the weight. And we have an upward force because since it is flying in the air, so there must be something in the upward direction that is lifting it, and we call that a lift force. And we just in the last slide saw that that is because of that Bernoulli's principle. And since the airplane is moving forward, and we call this forward force as thrust force, and we encounter something called a drag. That is the air resistance. Basically, we don't want it, but since the air is there and we are displacing the air and putting some extra volume into that vicinity, so we are going to, of course, get some resistance. And the air resistance here we call drag. So we have to cater this drag somehow as well. So these are the four basic forces that act on an aeroplane to vertical and horizontal component of forces. So for the plane to rise, if we want the plane to rise up to the sky, so then the lift force, the upward force, must be greater than the downward force, which is the weight. If we want the plane to fall towards the earth, we want it to descend from the sky, then we need the downward force, which is the weight, to be greater than this lift force. So there's an upward force, there's a downward force. So whatever force is more strong, the plane will go into the direction of that force. So if we want to slow down the plane, we need more drag force. We would do something that would increase the air resistance, and we will slow down our engines, will reduce the thrust. If we want the plane to accelerate, so we'll do something to reduce the drag and we will increase our thrust. So this is how our basic motions of a aeroplane work. Okay, so this is one of the most important parts of today's lecture, that we understand the basic motions of this any kind of airplane with that has wings, right? Any shape, any kind, if it has wings, so it is working on this phenomena. So the three axes referred to as longitudinal, lateral, and vertical. Okay, so we have this longitudinal axis. So there is our vertical axis, and then we have this lateral axis. So we define three axes that are perpendicular to each other. So at all of these three axes are facing each other at 90 degrees. Okay, so the others and intersect and the aircraft center of gravity. So if we say that all of these are intersecting at this very center of that aeroplane, the center of gravity, then what we can define is that motions around the longitudinal, lateral, and vertical axis are referred to as roll, pitch, and yaw. So if we think, if we can see this animation, so we'll see, okay, so this vertical rotation indicated by this blue arrow, which rotates the aeroplane towards this clockwise or anti-clockwise direction, that is called the yaw axis. Okay, so if we are rotating the uh, plane like this in this along the vertical axis, then we will call that as yaw axis. Okay, so this is the yaw moment of the plane. If we are ascending the drone upwards or descending towards the ground, then that moment is going to be across this pitch angle, this red angle, which is the lateral axis. Okay, so again, let's see that we are defining this pitch angle as this upward and downward motion across this lateral axis, and we call this up and down motion to be pitch. So this is the pitch, and the lateral axis is basically the plane to the right side or to the left side, we are performing this roll line. Okay, so if we are having a moment across this, if we have uh, If we have movement across this longitudinal axis, then that is the roll angle. If we have the uh, well, motion around the vertical axis, we have this yaw angle. And if we have the motion across this lateral axis, then we perform the pitch angle. So the pitch is forward, backward, ascending or descending moment of the plane, and this yaw axis is the rotation of the plane in the clockwise or anti-clockwise direction, and this longitudinal is the left and right motion of the plane. So we have roll, pitch, and yaw, three things that we can work with during any kind of design processes. So moving on. So let's talk about the individual parts. So we can define the overall control structure of an aircraft into two main groups. Okay. So the first is this primary flight control, and then the second is this secondary flight control. So let's have a look at this primary flight control. So in primary flight control, I hope I am audible and the screen is visible to everyone. Okay, so if we see the primary flight controls, we have elevators. What are these elevators? These are with the horizontal stabilizers at the tail end of the plane. So these are surfaces highlighted with this blue color. So these can move up and down, and they do change the motion of the plane in a certain direction. We'll come to that later on. Then we have these ailerons. These are the major portions in the main.
Abdullah, we can't see the presentation. Can you hear me? It seems like your connection keeps cutting out. There we go.
Yes, I don't know why the Zoom closes on its own. Am I audible now?
Yes, yes, we can see the presentation now.
Okay, okay, great. I hope that you did. I was not offline for a long time. Okay. So we were talking about these elevator, ailerons, and rudders. So elevators are something that is attached with this, its surface that is attached with the horizontal stabilizers of the plane, and it is at the back side. Then we have ailerons, which is this part of the main wings. So it moves and it changes direction of the plane as well. And then we have this something called this rudder. Okay, so rudder is attached to the vertical stabilizer tail end of the plane. So it moves in a certain direction as well. So these are the main three surfaces that perform the major main course keeping action of the plane. So by changing these, we can have forward, backward, up, down, sorry, not forward, backward, up, down, left, right, and rotation motion of the plane. Okay. Now, if we see the secondary flight control surfaces, well, we have something called slat, which is the front part of the wing. They do contribute, but somehow very little in a different direction. And we have something called the flaps. These are the back side, and these are special surfaces attached to the next to the aileron part. And we have flaps and spoilers. These are two different surfaces attached to the wing. And so it keeps on closing again and again. So just give me a minute. I'll restart the system to see if we can get this fixed. So kindly, I'll join in 1 minute.
Hey, Abdullah Mughis is coming back online. He just came back in, getting ready to go, having connection problems. That's the internet for you. Abdullah, are you able to reconnect back in? Start the presentation?
Hi, sir. Sorry for the delay. I apologize. I don't know why this is happening. The Zoom keeps on cutting off, right? So I'm unsure
Yeah,
of
maybe
what's
maybe don't
happening.
show your
I
screen.
hope I'm audible now. I'm
Don't
just
show your
assuming
video.
audible
Just show your screen.
to everyone.
I'm gonna turn off your video. Hopefully, looks like you might be cutting out again. Yeah, don't turn on your video. Don't turn on your video because it's gonna like hit the limits of your bandwidth. Yeah, let me turn off your video.
Am I audible?
Yeah, if you can turn off your video, don't turn on your video. We can see your presentation and just listen to you. So I guess while we're waiting, I think, is he here? There you are. Yeah, don't turn on your video. Just go ahead and put on your presentation. So yeah, we're going to be starting up so that the students can teach these live classes. So if you have something really interesting that you want to teach, maybe some of your research or some ideas that you're working on, contact me and send me a PowerPoint presentation of the class that you would want to teach. So we're going to have students start teaching some of these live classes. So that's just a little announcement. And it may be probably at least a month before you would start teaching. But it could be earlier. We don't know yet if there's an opening. If there's an opening in the schedule. But yeah, we know our students have a lot of really interesting topics to teach, and we want to give you the experience. Okay. Abdul, I don't see you anymore. So let me put my email into chat here. So that if you're interested in teaching a live class, go ahead and contact me. And it's basically you're going to be teaching for about 30, 35 minutes, 40 minutes, and then there's like 20 minutes of questions and answers at the end. If you have any questions in the meantime, go ahead and there we see Abdullah. So Abdullah, don't turn on your video. Turn off your video. That's what's killing your connection. There you go. Yeah, just do your presentation. Oh, you need to be co-host.
Hi, sorry. Yes, thank you. I think the internet connection at this point is not very good. Apologies for the delay.
There's always something, in the last couple of months, there's something going on with the internet that it's not as stable as it used to be globally.
Yeah, yeah. So I apologize for the delay. We can just, I hope my screen is visible. We can just continue from where we
Yep,
left off.
looking good so far.
Okay, great. Okay, so we have these primary control surfaces, and then we have these secondary flight control surfaces. We have the flaps, we have the spoiler that is attached to the. So these the secondary flight control surfaces are the parts of the aeroplane that are controlling the very individual small portions of the whole volume that is occupying this machine. Okay, so they make very small changes. So these are primary control surfaces. These are the ones that ailerons, elevators, and rudder that make the major changes, the major well, the dynamics change of the motions of the plane, right? Okay, so well, let's see to this first primary uh, primary surface that is this elevator. So if we see, so at the tail side, so we have some surface which is indicated by this black box. So it is moving up and down, and in accordance with that, you can see the plane moves in an up and or down direction. Okay, so that surface is called this elevator surface. So an elevator is mounted on the back edge of the horizontal stabilizer. So this horizontal surface indicated by this orange surface is the horizontal stabilizer, and elevator is attached to the back end of this horizontal stabilizer. So the elevators move together, they move up or down. If they move down, the when the pilot pulls the stick backward, the elevators go up while nose of the aircraft goes down and vice versa. So if these elevators are pushed downwards, the plane will move upward. If they are moved upward, so the plane will move downwards. Okay, so this is how they work. So the pilot has uh, of- some kind of stick that gives the commands to these elevators. So if he pulls the stick backwards, so these elevators at the back of the aeroplane will move to the back side, and similarly to the other side. So I have included another picture as well, which does indicate uh, how this up and down motion is controlled by this elevator angle of the surface that is mechanically attached to the system. So these movements are usually done not using some electric motor, but rather using some hydraulic system because of these surfaces have huge weights in big planes. Okay. So then we have this second surface, which is the ailerons. So ailerons are on the main side wings. So they are at the far end of each wing. So we move them in opposite directions. So remember in elevators, we were moving them in the same direction. Both were moving downwards or both were moving upwards. But the ailerons, they have to be well, opposite to each other. So if one is moving downwards, the other must move upward. So ailerons are mounted on the trailing edge of each wing. They move opposite in directions. So when the pilot wants to move to the plane to the left side, what happens is that the left aileron goes up and the right goes down. So the plane will move to the left side. Okay. So well, uh, the summary here would be if you want to plane to go to the left side, you move the left aileron up, and the if you want to move it to the right side, you move the right aileron upwards. A raised aileron reduces lifts on the upward aileron, and a lowered one increases lift. So how do we get this rotation in the first place? It is like this that if we lift this left side aileron, then what would happen is that we would face a little less lift at this side. So if we take this surface up, we are facing less lift. So this is going to drop a little. So if it drops a little and we are going to move this aileron a little towards the downside, and we're going to get more lift. So on the right side, we're getting more lift. On the left side, we're getting left lift. So it is obviously going to turn from the right to the left in an anti-clockwise direction. And we would call this the roll angle. Aileron controls the roll angle. So by changing the degree of rotation of these ailerons, we can determine how sharp turn we are going to take. Okay. So this aileron surfaces basically control the roll angle of the aircraft system. Okay. Then we have this rudder. Okay. So the rudder is at the far back end in the vertical stabilizer of the drone. So it is mounted on the back edge of the fin. Okay. So what it is doing is that its movement changes the direction of the aircraft in a clockwise or anti-clockwise direction. So it is basically rotating the aeroplane in a left or right motion. Okay, we are not having any kind of ascent or descent, which is the pitch angle. We are not having any kind of turns, which is the roll angle, but rather we are just changing the direction, okay, without taking any kind of roll or tiltations. So that is basically the yaw angle. So when the pilot pushes the left pedal, the rudder deflects. So we have two kinds of pedals. One is for forward, backward, left right motion, and the other pedal similar to that. Well, we use that to rotate the aircraft system in a clockwise or anti-clockwise direction. So deflecting the rudder right pushes the tail left and causes the nose to yaw right. So yawing right indicates here that we would be moving in the clockwise direction. Centering the rudder pedal returns the rudder to neutral and stop the yaw. So we just make this pilot stick come to the center point and it will stop this yaw axis movement. Okay. So then we have these secondary flight controls. So these are these small surfaces which do contribute to the motion and they change the air, but this is kind of like a fine-tuning mechanism of the major surfaces. So these are the flap and slat motions. So we have these ailerons. These are this surface. This green color surface is the major one which is going to rotate the aircraft system in the roll angle direction, which is turning right or turning left, but we do have these flaps and slat surfaces. Flap in this red motion right next to the aileron, and then these flap surfaces. If we want to suddenly the increase the motion to some extent, we sometimes use these surfaces. They do contribute to the change in the motion, but the contribution is quite low. So similarly, we have these spoilers. These are attached to this uh, wing surface of the basically they would be at this part, right? So in this actual uh, video of the aeroplane, so the rightmost end part is that aileron, and this would be the flap, and on the front side would be the slat, and this up and down motion is this spoilers. So they can be used for air brakes as well. So then we have these frames. So these are very small surfaces extended to that original surface. So all of that green color is that elevator control, and we have that small portion of that called the trim tabs. So that is again fine tuning that motion to a very great extent. So we have these secondary flight control surfaces that do contribute very little to the original motion, but they can make the aircraft system obey the commands of the pilot to a great accuracy. So using these secondary flight control surfaces. So if we think about it, all we have to do is just change the directions of these surfaces, and the aircraft system will have rotations in accordance with the rotation that you just did. Okay. So now it's about the question that how do we know which surface to rotate and with what extent? So I have a detailed diagram here that explains. the details. So we have this blue color indicated the spoilers. We have this ailerons, and we do understand that there is a roll motion, there is a yaw motion, and there is a pitch motion. And we just saw that in the horizontal stabilizers we have elevators, and in the vertical stabilizer we have this rudder. Okay, so we have a lot of stuff in an aeroplane. We have the control sticks where the pilot is placed, and we have the rudder pedals which will control the yaw axis. We have a lot of flight computers, the sensors, the actuators, and a lot of detail in an aircraft system. So we have a lot of sensors that detect every small change in motion. And what happens is this. So the sequence of events that occur are these, that we have a pilot who gives command to the aircraft system. So let's say he wants to turn left. So the pilot will just move his stick towards the left side and expect the drone and expect the aircraft to turn left. What would happen is that the stick will give command to the flight controllers. Okay, so this flight control will have all that complex control engineering behind it, right? So this flight controller will give signal to the actuators, and those actuators are actually going to, well, rotate the surfaces physically, the surfaces onto this aircraft. And in response to those rotated surfaces, the aircraft is going to move towards the left side. What we do next is that we place some kinds of sensors onto these control surfaces, and we get the feedback from the sensors that we wanted the aircraft to go left. Did it go left? We wanted to raise the elevator a little. Did the elevator got raised? Was it raised, right? So we have these feedback sensors attached to these surfaces that ensure that we get a feedback about the actual motion of the physical plane, because there might be some kind of damage to that wing or to some kind of system. So we put sensors everywhere to determine what is happening outside the airplane in air. Okay, so now let's talk about that nature's attack. So this is microbus. So on the right hand side, I hope you can see the video. So this is a microbus. So what happens is that, well, sudden violent downward wind from a thunderstorm hits the aircraft, especially during takeoff or landing. It can instantly push the aircraft towards the ground. So the aircraft was moving fine, nice and fine. Now it suddenly encounters the microburst and bang, it comes down. The pilot does not make it come down. So the airplane, while it is moving in the sky, can got can get caught up in this microburst, and it becomes very difficult for the pilots to control the dynamics of the aircraft. So most of the time we do get affected, and in the past we were getting a lot of incidents whenever the plane was in contact with this microburst. So aircraft is already quite low if this happens during a landing process, because microbursts, well, they occur at low heights as well. So there is very little time to recover, and once there is a sudden descent, the probability of crash would be quite high. So we encounter a sharp drop in lift force. Okay, we have very confusing winds, and the pilot input is not sometimes good enough without technology. So we somehow try to use the commands of the pilot along with our own autonomous technology to cater for these microbursts and other extreme weather phenomena. So if we define the problem, we can say that a microburst is a shaft of cold air that plunges to the ground from high up in the atmosphere, often in thunderstorms or sometimes other cases as well. A low-flying airplane is significantly affected by the microburst. So since the microburst was also at low altitude, but If the airplane is within the vicinity of this microburst, so it is going to, well, cause it to descend in a very short period of time. And if the airplane is near the Earth's surface, it is going to hit it. So the pitch angle, which is the up and down motion of the aircraft, the pitch angle of the aircraft varies by a huge magnitude, causing the airplane to crash. Right? So this is the problem that we can define, and these are some of the videos of once we lose control of the pitch angle, well, that is the up and down motion. So pitch angle or the elevator control is the most important, okay? Because without that, we are going to go down. Well, if there is no lift, well, what's going to happen? Okay. So these are some of the videos of once you get the plane out of control. Of course, the pilot is trying to save it, but those surfaces are just not a wing. So well, we do get a catastrophic event. So while it is in the vicinity, so you see there is a sudden descent, and if it does not have time to recover once it is outside the microbus, so it will crash. So these microbursts are sometimes few miles long as well. So these are not very short; they're quite expanded. Uh, they have a lot of area. Okay, so these microbursts are very confusing. So what happens is that the tailwind becomes the headwind, and the headwind becomes the tailwind. We suddenly have a lot of very weird motion of airs that we do not understand, and our normal physics and the control concepts that we implemented in our flight controller, well, they just don't make sense. Okay, so hence the airplane is forced downwards rapidly, and its pitch angle increases sharply as the pilot tries to recover. Okay, so once it is outside, the pilot is trying to pull it up. So a lot of different weird stuff happens. So we need some kind of autonomous system. So what happens is that we full thrust immediately, and we try to regain our speed. We know, well, the pilot knows ways to rebuild lift. So we try the engines to have the maximum capacity, and we try to lift the aircraft back to the sky. And if there's a landing process nearby, we just abort it, and we first get out of this microbus system. And once we are outside the vicinity of this catastrophic uh, condition, then we can have that landing process. So if you see that once the airplane is outside, so the degree of variation is very small. So once it is not within the vicinity of this microburst, the variation is 0 to 1.4 degrees. But once it gets inside, so the angle varies from 0 to 40 degrees, that amount of angle. So the same amount of signal, same dynamics, and same commands from the pilot will have a huge different kind of impact once it is within the vicinity and outside it. So when it was outside, if there was some kind of variation, it was between 1 degrees, around 1 degrees. But once it was in the vicinity, so the average variation would be around about 30 to 40 degrees. And the maximum allowed pitch angle for commercial airport is 30 degrees. So if the commercial airplane goes into the vicinity of this well, uh, microbus. So we expect a very bad outcome. So what we normally do is that we get some kind of data of the air, and we try to put that in a computer, and we resimulate that. Okay, so this signal represents the effects of a microburst. Then what we do is we use our computers to simulate, okay, what's going to happen by giving this microburst, and we get some kind of output results. So this is the process of what is happening. So the pilot gives the signal forward, backward, left, right. So do we have this power electronics that convert this mechanical pilot signal to the electrical signals, and we give it to these signals are converted, and we give it to these controllers. This controller gives the signals to the physical surfaces, the elevators and stuff like that. And then in accordance with that, this aircraft moves in an upward downward direction, and we note these signals and readings to determine if the things are happening as per our requirement. Okay, so we get some mathematical modeling of the system to simulate it. We can have a mathematical representation of this elevator motion using the defined equation that is for uh, the design purposes. Okay, so like I always say that we can always represent everything in mathematics. If we can't, we don't uh, have enough knowledge about it. So we do have good enough knowledge about the aircraft systems. So to summarize, this is what is happening where the pilot gives the reference signal, which is the desired signal using its stick. The controller controls the actuators, which will control the physical surfaces, the elevators, the rudders, the primary surfaces, or they can control the secondary as well. And well, we have this Dryden Gust model in the simulation that represents the microbus, and we can simulate all of these things in a computer and see what's going to happen if our the specific aircraft goes into the microbus. So rather than having to do the actual experiment with actual aircraft, what we can do is that we can always simulate and get our things done. So, so yeah. So again, that is the same details that what we do is well, this is the basic control closed loop control engineering concept of how this surface is controlled. So like I previously told that once the controller gives signals to these physical surfaces, we somehow try to put some kind of sensors onto it, and we uh, compare our reading with these sensors that is it giving the reading that we want. So we wanted the elevator to tilt to 12 degrees. So the sensor will tell if it has physically actually tilted to 12 degrees or there is some kind of issue in that rotation. Okay. So that is the complete control loop closed diagram. That is basically the engineering part. So you can always ask questions about it. Okay. And I have included some kind of literature review as well that the control algorithms the researchers have been doing to well control the actual motions, the roll pitch yaw motions of this aircraft system. So there have been a lot of work going on. So they designed this Legio-based model predictive control. They designed this fractional order proportional integral derivative controller, and a lot of different other kind of research work has been well, going on. So this is direct force controller, fuzzy proportional integral derivative, linear quadratic regulator, and a lot of different kind of work have been going on throughout the world. So well, what we do is that we can have this Doppler radar that can detect microburst before it happens. So we do understand that we're getting into a microburst, so the pilot can get mentally ready or avoid it in the first place. So we have onboard wind shearing warning system that alerts the pilot, okay, we are going to enter in the vicinity of a microburst. And we then introduce these auto throttles and fly-by-wires for instant corrective actions. So instead of having to do it manually, having to control this aircraft manually, we can have this autonomous functions using this uh, control technologies. So we do have some aerodynamic advantages if we can get a good design. So wing shape produces lift even in disturbed air. That is advantage of an aircraft that has wings. So flap and sides boost lift when speed is low. So these secondary control surfaces, they do contribute they boost the lift even when the speed is low. Strong engine overcomes sudden drag. So the drag, the resistance we encounter, we just increase the throttle, we move it forward, engine at full speed, and we get better results. So normally what we do is that we try to simulate these things and we give it to the pilot so they can, well, train repeatedly for microbus scenarios. So that would increase the survival rate if they encounter it in real life. So flying is these days, flying is one of the safest modes of travel because of all this engineering that we do understand. And whatever problem that we face, we usually come up with a solution. And for this microbus problem, we have come up with very, very good solutions. So the science of flight continues to evolve with new problems, comes new solutions. So in conclusion, in today's lecture, we have learned that aircraft ability depends on precise control of these primary surfaces, the elevators, the ailerons, and the rudder, and we need to control the pitch, roll, and yaw. Okay, microburst causes rapid loss of lift, very rapid loss of lift, and it makes uh, the aircraft to go up or down, usually in the downward direction. So strong aerodynamic design and high response engines can give us a good shot for surviving that problem. So pilot reaction time is insufficient, and we do need some kind of automatic control system in these scenarios. So some modern controllers are continuously improving the performance of these aircraft systems. And once we design these control systems, so we simulate it and we design these simulators in which these pilots keep on training themselves so they can have the better idea of an actual scenario. So continuous research in flight control and weather sensing will further enhance aviation safety in the future. So these are some of the references where the data was taken, and now we can move on to the question answer session. Thank you.